Materials can be engineered to be responsive, creating new type of materials known as responsive materials or smart materials. These materials are designed to have properties which allow them to transform under the influence of external stimuli like temperature, moisture, electric fields, stress, etc. In other words, they have the ability to respond to their surroundings. These are a few commonly used materials explored in the field of design and research for transformation, categorized on the basis of stimuli and response. SuperAbsorbant polymers are highly absorbent natural or synthetic polymeric chains. These long molecule chains can typically expand up to 10 to 1000 times their weight over a period of time. Hydrogels are commonly used to make contact lenses, diapers, for water retention, wound dressing, drug delivery, and scaffolds for tissue engineering. There are many different types of hydrogels and are based on various factors such as stimuli, response time, degree of swelling, shape, and strength. The domain of each of these parameters is flexible and can be embedded during manufacturing. Input stimuli that hydrogel responds to are water, temperature, pH, magnetic field, light, pressure, sound, and other chemicals. Although hydrogel respond to many different types of stimuli, the one used for this project responds to water. This project looks at three distinct properties of hydrogel, namely optical, thermal, and mechanical.
Water-based color pigments dissipate in hydrogels like ink dissipates in water. Hydrogels act as lenses, distorting the views, creating unique filters between spaces. Swollen hydrogels share the same refractive index as that of water. This occurs due to the change in the refraction boundary between air and water, maintaining the direction of light. Focus is a prototype that demonstrates the gradient of distortion created by hydrogels in water. This is achieved by changing the level of water over time. push is a prototype that changes the level of hydrogels, submerging them in water when pushed, creating a pocket of visibility amongst distortion. Press uses force to create a transformation from distortion to transparency. This occurs due to the increase in the surface area of hydrogels in contact with its enclosure. Since swollen hydrogels are 95% water, they have the same rate of evaporation, which is 0.6 kilocalories per gram. Therefore, hydrogels can be used for evaporative cooling. Their solid state allows for ease of application, installation, and maintenance. They can undergo thousands of swelling cycles, making them durable. With the possibility of engineering hydrogels to the required swelling capacity and response time, one could achieve 4 days of evaporative cooling with just 4 hours of water supply, saving both water and energy loads. For this, understanding the spacing and volume of the hydrogel required was studied. Hydrogels can be threaded together to be placed in the required configuration without the need of an envelope, allowing maximum evaporative cooling. These panels can be placed at the external facade, absorbing both supplied water and rainwater to later give passive cooling to the space. Experiments with variable spacing were undertaken to measure the degree of evaporative cooling achieved by hydrogels. A temperature drop of up to 3 degrees Celsius was recorded in our experiments. A composite assembly of hydrogel and burlap was also explored to further enhance the cooling effect. Recent studies undertaken at the School of IAC using hydrogel ceramic composite called hydroceramic for evaporative cooling show promising results of reducing the temperature up to 5 degrees Celsius, in turn reducing the cooling load by almost 28%.
Mechanical properties of hydrogel allow the material to be used as an actuator. To quantify the number of hydrogels needed to actuate a mechanism, the compressive force exerted by different types of hydrogels was calculated using the Instron machine. Maximum force exerted by 100 hydrogels was 40 newtons, by 10 large hydrogels 4 newtons, 8 cubes was 6 newtons, 11.46 grams of powder was 5.5 newtons. Medium-sized hydrogels exerted the maximum force per gram. Hydrofins is a component which uses mechanical properties of hydrogel to actuate fins. Hydrogel balls are used to push the pivoted arm of the component, which enables rotation of the fins, rendering them open. This component consists of chamber for hydrogel, catchment for rainwater, and a torsion spring to push back the arm to its initial state once the balls deswell. Peak is a prototype of a responsive skin actuated using hydrogel housed in a linear actuator. This material has the capacity to create a layer of interaction between spaces. Dead walls and screens can be made more engaging, creating tangible interfaces. For example, display panels in exhibition spaces can be made more interactive by creating a need for engagement to disclose information. Static partition between people can be more engaging and interactive. The level of privacy can be controlled by the users, giving them the ability to engage and disengage at will. This can easily be achieved by strategic use of hydrogels. Panels that generate curiosity through distortion, revealing itself based on proximity or time. Hydrogels can be used to create dynamic spaces with changing shape and texture, giving a unique experience of the same space at different time of the day. This space change can further be controlled by added restrictions and limitations to its growth. This can also be applied to existing spaces. Designers can use this material to create skins responsive to their environment. Example, facades that close themselves when it rains, shade itself from harsh sun, etc. Control of such skins can also be given in the hands of the user, creating facades with the ability to change based on interior activities, like watering of plants or turning on of a water line. These facades therefore have the ability to project interior activities on exterior walls. Such local deformations can create global transformation, resulting in dynamic facade through user participation. The architect will soon be able to specify the properties and performance of a material as per his design. The exploration done in this project is barely scratching the surface of the potential this material holds. There is constant development of this material, making it stronger, rapid, easy to fabricate. Although the hydrogels we have at our disposal do not have these properties, knowledge of ongoing research can help us foresee its application in the future.